Okay, great. So I'm Jen Cano. I'm a professor at Stony Brook University. I think there's someone here from Stony Brook, so maybe please introduce yourself later. And I'm also a research scientist at the Flatiron Institute in New York City. So I should have said, so the goal of this lecture is to try to introduce you to a new phase of matter, which is called a topological insulator, which is one of the main focuses of my research and the focus of our program at KITP. Before getting into that, I think I had the same idea as Shimao. I wanted to step back and say, what is the goal of condensed matter physics? So everyone in our program is a condensed matter physicist. Most of us are theorists. So we use a lot of math and computational simulations to study materials. And then we also have a few experimentalists who are also here to tell us about their experiments. And we try to convince them to carry out some of the ideas that we have. And they tell us, no, that's not a good idea. Then we go back and think about it again. But stepping back from that, so condensed matter physics, as Shimao was just saying, the fundamental goal of condensed matter physics is to understand different phases of matter. And I think probably usually when you think of a phase of matter, you think solid, liquid, gas. So I have some of the same figures maybe as Shimao, but this one is actually kind of nice. This is actually a surf scene at Campus Point, which is right outside the building here. So maybe you can check it out if you have some free time. But this classification of solid, liquid, and gas is only one way we can classify phases, which is how are the atoms arranged? Are they ordered or are they disordered? And we could detect some of that order by, say, applying pressure. Solids don't compress, gases compress. But there's other ways also that we could define different phases. So we can also ask, how do electrons move around in a crystal? So that's pretty much what's going to be the focus of this talk. So this is the distinction between a metal and an insulator. And then we could dig even deeper and say, how are the spins inside of electrons arranged in a crystal? And so this gives us all sorts of magnetic phases. So there's a ferromagnet where spins are all aligned with each other, antiferromagnets where they're anti-aligned. I've also drawn a picture here of a skyrmion lattice. This is kind of a more exotic spin texture where the spins are winding around in kind of funny ways. And then also the quantum spin liquid, which is going to be the topic of Leon's talk at the end of the day. So there's all sorts of exotic phases, and what we mean by phase of matter changes when we ask what degree of freedom are we trying to classify, and also how are we trying to probe it, like with pressure, with transport, or maybe with a magnetic field. And so it's precisely all these different possibilities that comprise the quantum universe. In this talk, we can stay a little bit simpler, and so I'm just going to focus on the metal insulator, the transport characterizations of materials, of solids, and then, like I said, try to introduce you to some new phase of matter, which is called a topological insulator. Okay, so metal versus insulator. Probably most people are familiar with this concept, but I just wanted to start from the beginning. So a metal conducts electricity, and so the way that we can think of this from a practical perspective is we can attach two leads, i.e. two wires, put a voltage across those wires, and a current will flow. And we know that a current is flowing because we can put a light bulb there and we can see if the light bulb turns on. So that's kind of a practical probe of a metal. If we took an insulator instead and we put two leads on it and put a voltage across those leads, current won't flow. So that gives us a practical distinction of metal versus insulator. So a topological insulator, from a phenomenological perspective, is a hybrid of this. So it has a very weird property, which is that it is insulating on the inside of the material and conducting on its surfaces. So it's kind of a combination. And so you might think to yourself, well, this seems kind of trivial. I could make this at home. I could take a block of wood and I could wrap it in a piece of tinfoil. That would be insulating on the inside and it would be conducting on its surface. But this is actually not what I mean, because if you did such an experiment and then you cut it in half, you would see the true colors of what you've done, which is you've just taken a block of wood and wrapped it in tinfoil. And the topological insulator, so it has a different property than this, which is that if you cut it in half, you create a new surface, and that new surface is still conducting. And so this is, in some sense, this is kind of like a magnet. You can think of a magnet, it has a north pole and a south pole. And you might think, if I cut it in half, I could separate these poles. But you know that you can never do that. Every time you cut it in half, you make a new north pole and a new south pole. The north and south pole are intrinsically part of the whole of the magnet. That's kind of how the topological insulator works. The surface of it is intrinsically part of the bulk. It can't exist by itself. And because of this property, you can't skim off the surface and look at it. Actually, the surface is kind of its own metal, and it has different properties than normal metals will have because it's intrinsically part of this new phase of matter where the surface and the bulk are tied together. So I can give a couple of examples of how this works. They're not examples that you've probably seen at home, but hopefully I can provide a few cartoons that motivate how this works. So the first example is called the quantum Hall effect. So the quantum Hall effect is a phase of matter that exists in 2 dimensions. So I also want to say something about dimensions. So as physicists, especially theoretical physicists, we're privileged to talk about any dimension that we want. And you may have heard, various theories of the universe, 10 dimensions. Okay, I don't know about all of that. But what I want to say is that actually 1, 2, and 3 dimensions are things that we actually can make, and these things exist in nature. So 2-dimensional materials exist. There was a great teachers conference on graphene. Probably some of you 20-year people have been to that. So graphene is actually a 2-dimensional material. You can basically think if I have some crystal and I keep slimming it down, graphene is just 1 atom thick. So it's literally just a bunch of carbon atoms. They're only connected in a plane, and they don't have any 3rd dimension. So 2-dimensional materials exist. Also, 1-dimensional materials exist. And so we're free to talk about these things without even being that imaginative. So if you take a 2D material and you apply a perpendicular electric field, so that's actually what this picture is meant to show. I apply a perpendicular electric field, and then I apply a voltage which is going across this material. Current flows in the perpendicular direction to that. And that's called the that's called the Hall effect. It becomes quantized in very large fields. And this actually always happens as you put on a very large magnetic field. So how does this relate to my picture of edge conduction? Well, what happens when you have a really large magnetic field is that electrons get trapped moving in circles. So you know that if you have a magnetic field and you have a charged object, it'll move around and it feels a force perpendicular to its motion. So if an electron starts moving in a circle, it'll keep moving in circles. We call these things cyclotron orbits. So if I have my 2D material and I have 2 of these orbits on the inside of the material and they're next to each other, you can see that one electron will move in a circle pointing downwards, this one is pointing upwards. So if these things are next to each other, they don't generate any net current. There's no net flow of electrons. But at the edge of the material, something different happens. If you think of these circular orbits, when they hit the edge, they'll actually bounce around. And they only bounce in one direction because the magnetic field gives them that preferred direction. And so in a quantum Hall system, the inside is more or less inert, but on the boundaries, you have electrons that can move only in one direction. And so it has kind of a 1D channel for conduction on the edge of this 2-dimensional system. That's what makes it different than a normal 1D wire. In a normal 1D wire, electrons can scatter left and right. But here, on one edge, they always move in one direction. On the other edge, they move in the other direction. So this is very much akin to a one-way street. And what makes this so interesting is that this kind of 1D transport is very robust because electrons can't backscatter. So in a normal metal, if I had like a wire and I had electrons flowing and they encountered some kind of disorder, they would hit it and they might go backwards. And so in a very disordered material, you wouldn't expect to be able to have net current flow because electrons scatter off of each other too much and they'd be trapped. I'll take your question in 1 second. But in this case, when you can only flow in one direction, if you have some dirt at the edge, like I've drawn here, there's no channel for electrons to go backwards, and so they just go around it. And so this gives you very robust transport. Question?
I'm just curious.
Yeah.
Do you do a positive charge transport for your current, or use electrons?
Hopefully I'm not going to write anything that requires a sign, but but I would always think about electrons moving. And actually the Hall effect, when they first measured it, this was actually an experiment that distinguished whether electrons or holes would move, because they could actually see, basically the sign of the current would tell you whether there is positive charges moving or negative charges moving. So we should always think about kind of electrons moving, and atoms staying fixed. Yeah. Yeah. Yes, okay, good. So what I'm really thinking of is electrons, negatively charged electrons, flowing around the edges of a two-dimensional sample. So all the current is on the 1D edge, and this is different than a normal 1D wire because electrons only flow in one direction in this system. One edge is one direction, one edge is the other direction. And because of that directionality, it gives rise to a very robust current that isn't how should I say this? It's more robust against disorder than normal current would be. Yes?
What about edges?
Yes.
Does it continue around?
Yes, exactly. So I only drew two edges here, but yes, you should think of this as moving in a circle. In these experiments, usually you have like a lead at either end, and so then your circle gets kind of ruined, but it would be precisely that. So I would take my two wires, I would attach a wire to this end and a wire to this end, so current would flow along this edge, and then come out my other wire. But if this system was sitting unperturbed, then yes, it would be moving around in a circle. Yeah. Yes? Okay. Yeah. Good. The Mobius strip is going to enter on a later slide, but I wasn't planning on having it enter here. Yeah. Okay. Interesting. Yeah. I guess in this case, you only have one edge. One thing that's going to be tricky for your Mobius strip is that we always need the magnetic field to be perpendicular. So that setup would be kind of weird, because you'd always need your magnetic field to be perpendicular to your Mobius strip, but your Mobius strip direction is turning around. So that sort of thing, I'm not positive how to implement it. Okay, great. These are great questions. Okay, so this is one example, but the magnetic field is playing a very important role, because if you ask yourself, how do the electrons know which way to go? Well, that's because of the magnetic field. It picked a direction. So I wanted to say that the quantum Hall effect has been studied a lot for the past 40 years or so, and it's been the subject of 3 Nobel Prizes. So the first 2 were more or less on quantum Hall and what's called fractional quantum Hall. But the third one, which is more recent, was asking the question, could I have this same effect without a magnetic field? And one way that you can do that is in a magnetic material. So in that case, you don't have to apply the field, but because you have a magnetic material, it's kind of intrinsically inside, and that's called the anomalous quantum Hall effect. But then you could further ask, if I have no magnetic field and no magnetic material, can I have some analog of this? And so this is our second 2D example. This is called the quantum spin Hall effect. And what happens here is that, so what this really cool picture is showing is that there's a spin down channel going in one direction and spin up in the other. So basically, it's like 2 copies of quantum Hall. Spin up moves one way and spin down moves the other way. And if you have no magnetic field and no magnetic impurities, your 2 spins can't scatter into each other. And so you also have a very robust current, but it's a spin current. The net current would be 0, but the 2 spins are moving oppositely. So again, it has the same, or at least hypothetically, it should have the same kind of robustness to disorder. And the great analog here is of the Autobahn. It's like if you can separate spin channels and they can't scatter off of each other, then traffic can move incredibly efficiently. Yes?
What about if you have superconductor?
This is actually great. So This sort of transport is analogous to a superconductor. So in a superconductor, current can flow without dissipation, and it does it in a different mechanism. Electrons kind of form pairs, and those pairs move in a special way. The quantum Hall effect is actually doing the same thing differently, but it also has what's called dissipationless current. So those edge currents flow without any dissipation, and that's precisely what makes them kind of so potentially useful for future technology, basically, because they can flow very efficiently. And that's actually kind of our motivation for trying to find topological phases without a magnetic field, because if we wanted to have any device that's utilizing these electrons that can flow very efficiently, we don't want to have them in a large magnetic field. We don't, want to have that in our pocket or our computer. So part of the kind of technological perspective on this field is what are the topological phases that can exist in zero magnetic field, and then also at room temperature, which is the much harder of the questions.
What if you have superconducting, superfluid helium? Does that have anything to do with it?
Yeah, so basically all of these superconductors and superfluids and also our quantum Hall edge are all kind of related to each other. What the difference is what are the types of particles that are condensing, or what are the types of particles that are kind of moving? And so the difference between a superconductor and a superfluid is whether you have charged electrons or neutral particles that are moving around. But they're different phases, but they have kind of some similar properties. Yeah. Okay, good. And so then let me just say something about 3D. So for a 3D topological insulator, kind of like this material, which is not a block of wood wrapped in tinfoil, but an intrinsically 3D phase, it also has a surface state. And then, so its surface will be a 2D metal, but it will be different than a normal 2D metal. It has the property that any electron moving with a particular momentum, every momentum has a particular spin associated with it. And so, so I drew this traffic circle to continue the traffic analogy. And basically you can think of if an electron has some spin, which is just like some direction, some vector corresponding to the direction cars are moving, then its spin would be like the tangent vector. So in other words, you can't, in a normal metal, you could have any momentum and any spin, but here momentum and spin are locked together. We call it spin momentum locking, and you can just think of, well, whatever the momentum is, then the spin is kind of pointing in the same direction as that. And this is different than a usual 2D metal, but it's not as easy to understand as these 1D edge channels. Okay, so then I just wanted to, I've been drawing a lot of cartoons, so I wanted to show some actual data. This is not my own data because I'm a theorist, but just to show a couple of examples. So going back to these 2D examples, so what this picture is, it's actually a surface scan of some material, which is like layers of this 2D topological insulator. And this thing that they call a step edge is a layer, it's like a stair. It's like where one layer ends and then the next layer begins. And so there's a little step there. And so that step is like the edge of the 2D topological insulator. And so you should be able to see current which is flowing there, even though the inside of this thing is insulating. And so, so this data is taken with a technique which is called scanning tunneling microscopy. And so what they do is they take a tip, and the tip has a current that flows between the tip and the sample. And so if your sample is metallic, a current will flow, and if it's insulating, basically it won't flow. And you can scan this tip over the surface, and so you can get a real space probe of where electrons can flow in your material. And so that's what this right-hand picture is showing. So the dark areas have no current, and the bright areas have current. And you can actually see that there's kind of this current which is flowing along this 1D step edge. So that's a way that you can actually visualize this edge current in real space, aside from the cartoon perspective. 3D is more challenging. And so the way that they image the 2D surface states of 3D topological insulators is with a technique called ARPES, angle resolved photo emission spectroscopy. So ARPES is basically shining light and then seeing it reflect out. And the light that you shine in, you have to know what its momentum is and what its energy is. And if you know those things and then you measure what comes out, you can figure out the momentum and energy of the electrons that it's scattered off of on the surface. And so just by conservation of energy. And so then you can actually kind of image, at any particular energy, you can image these surface states. So it's not clear, I think I haven't really said enough to make it clear what this picture is showing, but this picture is saying that at some particular energy, you have electrons at some momenta. These are two different momentum axes. And if they do spin-resolved ARPEs, they can see the spin of these, which are drawn in by these arrows, and they kind of see this little traffic circle, which is a unique feature of the electrons on the surface of the 3D topological insulator. You wouldn't see this sort of image if you looked at just a 2D metal. So that's how you can image these materials. So they do exist. That's my point. They actually do exist beyond the cartoons. I then want to show a little bit of why might we actually care about these materials? And so I can give you my own perspective. Why do I care? Well, when I was an undergrad student, I was taking a lot of physics and a lot of math courses, and I took a course in topology, and I was like, wow, this is really cool, but I'm not sure where this is going. Like, what are we doing with this? I don't see this as any application. But then my undergrad advisor turned me on to this idea of quantum computing, and actually there's some really exciting ideas for a topological quantum computer. And so in the topological quantum computer, the idea is that the excitations are not just electrons, they're actually kind of fractions of electrons. And if you want to perform operations in this topological quantum computer, you have to braid the electron or these non-electron excitations around each other and keep track of the braids that you make. And to keep track of them, you have to use the notion of topology. So I'll say more about topology later, but you have to keep track of these braids and whether they're trivial or not. And I thought this is just absolutely fascinating that this field of topology, which seems so abstract, could be applied to real materials. And so, you know, at that point in time, I thought, well, I want to do a PhD and learn about this. And so that's actually what I did. I came to UCSB for my PhD and learned a lot more about different types of topological materials. So I should say that, there's many platforms for quantum computing, and that's not the subject of this conference. But this particular platform of topological quantum computing is something that is being pursued by Microsoft, and they had a research group which was at the UCSB campus that I had a privilege of being part of. So that's the connection to UCSB and also one of the applications of these materials. A second application is what I alluded to before, energy efficient electronics. So this is kind of a bit more practical. If we have these edge states of 2D topological insulators and they can flow without dissipation, this would be very useful to have in any sort of technological application. But of course, we want to realize it without a large magnetic field and at room temperature. And so that's kind of where the materials study of topological materials comes in. What are the material platforms that are going to have that property? And then finally, another application is spintronics. And so spintronics is a combined word that comes from spin and electronics. And so the idea is that in electronics, you want to store or manipulate data using the electron charge. But in spintronics, you want to do the same thing, but with the electron spin. In order to control electron spin, well, you need some handle to control it. And so if you have this spin momentum locking, it seems possible then, since it's easier, maybe it's easier to control momentum than spin, that would give you another handle by which you could control electron spin. So there's some branch of research where people are looking into, can we use topological insulators for spintronic applications? Okay, good. So those are my applications. Again, I'm kind of more of a math person. I don't really study these applications, but I think it's interesting to remember that, you know, for all the research that we're doing, that there is some end goal, especially since we use a lot of federal funding for this research. And I think there's some really practical applications that can come out of this. So now in the kind of second half of the talk, or last 1/3, I wanted to go into a little bit more of the theory behind these materials. So I'm going to try to explain what we call a band structure. So a band structure tells us about the energy levels of electrons inside of a crystal. So I'll explain that. that gives us a way that we can characterize which materials will be metals and which will be insulators, and then which will be our topological insulators. I'll then show a slide, what is topology, although I've already been alluding to it quite a bit. And then how do we combine these notions of topology to band structure? And then if there's any time left, I'll say something about a little bit of current research, my own research, and research topics related to the program. Okay, so what is a band structure? Like I said, a band structure tells us about the energy levels of electrons in a crystal. But first, to understand that, we need to remember what are the energy levels of electrons on a single atom. So those are precisely the energy levels of atomic orbitals. And so we classify these usually by principal quantum number. So that's usually what people call n. And then by their angular momentum, which is also called s, p, d, f orbitals. And then within each one of those angular momenta, we have the z component of angular momentum, because angular momentum is a vector, so you can look at different components of that vector. And so that tells us, for example, that if we have p orbitals, we can actually have px, py, and pz components. Similarly for d orbitals. And so this is kind of some cool table that I found, which visualizes many of these different types of orbitals. Okay, so I think people are kind of familiar with atomic orbitals a little bit, or some of you probably a lot. Now, if we take two, right, so then I just wanted to give some example just to jog the memory. So say we look at carbon. So carbon has atomic number 6. It has 6 electrons, and so you can think those 6 electrons are going to fill up, first they fill up the 1s orbital. We have 2 spins in every energy level. That's going to be important. So we take 2 electrons and fill the 1s orbital, 2 electrons and fill the 2s orbital, and then our remaining 2 electrons will partially fill this 2p orbital, etc. But now what happens if we take 2 atoms and put them next to each other? Well, then the orbitals on each atom don't remain the same. You bring the atoms next to each other, and the orbitals will form bonding and anti-bonding orbitals. Right, I think we have some chemistry teachers here. So for some people, this is probably extremely rudimentary, and then for others, like myself, we're coming back to chemistry after a long time, and it's more exciting in hindsight. So if we take 2 atoms and we bring them close together, they'll make bonding and anti-bonding orbitals. And we can think of these as being symmetric and anti-symmetric linear combinations of these electron wave functions that Shimao was talking about, is a different way of saying that. One will be lower in energy, one will be higher in energy. And having these orbitals actually saves energy, because suppose that each atom had 1 electron. The total energy of your system would just be twice the energy of this orbital. But now, if we make a bonding orbital, we can put 2 electrons in here instead of 1 each. And so that saves us energy. So making hybridized orbitals saves energy. And basically, delocalizing electrons over multiple atoms generically saves energy. Now, if we have 4 atoms, then we can do the same thing. We can make a completely symmetric bonding orbital, a completely anti-symmetric anti-bonding orbital. And of course, there's some conservation here. We always need to make 4 different orbitals. So there's 2 different orbitals in between, which are kind of a combination of symmetric and anti-symmetric. And the same thing is true if we started putting electrons in these orbitals. Well, if we didn't hybridize at all, then we'd have 4 electrons here. But in this bonding orbital, because we can put some electrons in the bonding orbital, which is at lower energy, then again, it saves us energy to put electrons here. So making these bonding or anti-bonding or hybrid orbitals like this, where electrons are shared over multiple atoms, ends up saving energy. Because electrons have kinetic energy and they kind of like to be delocalized. So now we can extrapolate what will happen if we have more atoms. We keep making more levels. And so I was trying to think how to show this. And so I'm going to make a plot which is showing the following. So it's energy levels, and these are just states that we have. So if we have 2 atoms, we have our bonding and anti-bonding orbital at 2 different energies. If I have 4 atoms, I have the totally bonding, totally anti-bonding, and then I have 2 more energy levels. You can then kind of extrapolate and say, if I have 6 atoms, I'm going to fill in some other different levels. And if I have 8 atoms, same thing. I'm going to be able to make more and more orbitals, and they keep hybridized orbitals, and they keep filling in different energies in between. Similarly, if I have 10 atoms, and what happens if you work this out using some very simple rudimentary assumptions is that these points fall on a cosine curve. And so the point would be that if you have bonding or anti-bonding orbitals of a discrete number of atoms, you get discrete energy levels, which is shown by these dots. But once you have a lot of atoms, like the 10 to the 23rd that Shimao was mentioning, these energy levels just become basically a continuum. And so we call these energy levels an energy band. We no longer talk about discrete bonding or anti-bonding orbitals. We just say there's a whole continuum of orbitals, and they have an energy which is shown by this cosine curve, and so that forms an energy band in a crystal. And you can think of this energy band as saying there's all these different states electrons can reside in. It would just be that my dots have merged into a continuum, but that's how the energy levels in a crystal are described. We stop talking about bonding, anti-bonding, we just make a continuous band.
Do you see that in the spectrum?
Oh yeah, I'm going to show some spectra. So, right, so this is also kind of a cartoon. Now, if that would be if I have just, say, s orbitals, but actually the p orbitals can also hybridize. So a crystal is going to have many of these energy bands, one band for s orbitals, some bands for p orbitals, some bands for d orbitals, and it's these bands together that comprise the band structure. And really what this is telling us is that in our crystal, if I look at some particular energy and I want to know, is there an energy, can electrons be at that energy? That's what this plot is showing us. Here's the energy, there's states at this energy. If I look at some other energy, there's no states at this energy. So that's kind of how I can read a plot like this. But in fact, these plots can be a lot more complicated because the s and the p orbitals can also hybridize with each other. So this is actually a plot of the band structure of graphene. That's the 2-dimensional material I mentioned earlier. What I like about this plot is that they colored the different bands to show what orbitals they're coming from. So for example, this band is both red and blue because it's actually showing that you get hybridized p and s orbitals. So in general, you get this kind of mess of bands. And we kind of sometimes refer to these as spaghetti plots because they really start to get jumbled up with each other. Okay, but actually we can still learn a lot from these band structures. And so the fundamental thing that we can learn is the distinction between metal versus insulator. So that's what I was trying to build up to. So how does this work? Well, we have all these energy levels. These are energy levels, but we then need to ask how many electrons are there and how do the electrons fill these levels? Some will be empty, some will be filled. So remember that each energy level can host 2 spins, spin up and spin down. So if you have an atom which has 1 electron per atom, it will only half fill this energy band. You can think of this as in our 2-atom molecule, we had just like the bonding and the anti-bonding orbital. And both of the electrons went into the bonding, and the anti-bonding was empty. Now in our crystal, it's the same thing. We have this whole continuum of states, but only the ones that are below the halfway point, which is my dashed line, only these states that are below and these states that are below will be occupied by electrons. All of these ones will be empty. And why does this give us a metal? Because this is the highest energy of the occupied state, and this is the lowest energy of the empty state. These energies are right next to each other. So if I attach my leads, electrons can easily flow from the occupied to the empty states. They just kind of flow through this band, and when they flow, that's what allows current to flow. Now, let me consider a different situation, which is what if I have 2 electrons per atom? Then I would completely fill this entire band. And now the highest energy occupied state is separated with an energy gap. We call this difference in between here the energy gap from the lowest empty state. So if I attach my 2 leads, electrons can't just flow, because in order to flow, they'd have to jump up here, and that takes a finite amount of energy. So if I apply a large enough voltage, I can get them to flow. They can hop up to this band. But in general, they won't flow. And so we then have a characterization of metal versus insulator. In these band structures, you need to know not just the structure, but how many electrons you have. If you have enough electrons to partially fill a band, then you get a metal. And if you have enough electrons to completely fill a band, then you get an insulator. That's the most fundamental distinction that we can read off of these band structures. There's lots of other stuff that you can read and lots of other measurements you can do, but this is kind of the most fundamental thing. Okay, yes?
Where do semiconductors come into play?
Yeah, good. So semiconductors exist in a couple of forms. One possibility for a semiconductor, it's basically that this energy gap is just really small. And so at like zero, this is how I defined it in my condensed matter physics class, at zero temperature, then you won't have current flow because they can't cross the gap. But at a finite temperature, you start to have some amplitude for electrons to sit in this band. Basically, finite temperature allows electrons to not be in their ground state, but to be in excited states. So at finite temperature, this band will be mostly full, but not completely, and this band will be mostly empty, but a little bit fill. And then the electrons that are sitting in the bottom of this can flow. So that's one way to define a semiconductor. It's an insulator at zero temperature, and it conducts at finite temperature.
And then
Yeah.
the current is flowing because all of the atoms
Yeah.
are sharing this band. Is that the idea?
Yeah. So there's a few different, I mean, on the most general level, current is flowing because, yes, each of these states is like spread out over many atoms, and you can easily kind of hop to another state which is empty, and that hopping allows you to flow. And when you apply your leads with a voltage difference, the voltage tells you which way you want to hop. So if you just have this material sitting here with no leads, there's no current flowing. Electrons can be a bit jumbled. But when I then apply leads, which kind of make electrons want to move, they can just very easily move, because next to every filled one is kind of an empty one, and it can just kind of flow. And you can think of the insulator when you have this whole band full. I mean, it's kind of, the insulator is kind of the equivalent of like a noble element. Like all of the orbitals are completely occupied. Electrons don't want to jump around. It takes a lot of energy to pull one out. Yeah. Okay, good. So metal versus insulator band structure. That's kind of our take-home message here. And I guess I have something more here, which is now some real band structures. Okay, people like this. So just to show, this is a band structure of gold. Gold is a metal, and the electrons are filled up to this dashed line. And so you can clearly see that it has this, even though it's complicated, you can still see that we partially filled this red band. And similarly, this is the band structure of diamond. It's an insulator. And so again, electrons are filled up to this line. So even though these bands are a jumble, you can still see that there's an energy gap between the top of this and the bottom of this. And so you can basically think of the insulator as having two separate jumbles of spaghetti, and the metal is like, you can't disentangle this because we have this kind of one strand that's kind of going all the way up. Right, and the other thing I wanted to say is actually, so making these band structure plots, there's a whole computational science which is devoted to this. There's another Nobel Prize by Walter Kohn, who was a professor at UCSB, which is laying the foundations of this theory. But I guess I just wanted to say that, in case you're curious, making plots like this is something that it's pretty well established. There's kind of packages of software where you can say, these are the atoms that I have in these positions, and the software has it built in that these are the atomic orbitals that are sitting on these atoms, and so you tell it, here's where my atoms are in a crystal, and it will kind of give you a plot like this. One of the interesting things is that these band structure plots they break down for certain types of materials where the Coulomb interaction is very strong. We can say more about what that means. And so one of the major research topics in condensed matter physics is kind of understanding when the band structure breaks down, why does it break down, what happens. So that's a little bit outside the scope of this talk, but I just kind of wanted to mention it. Okay, so right, metal versus insulator. That's our take-home message. Now let me just show one slide what is topology, and then we'll try to put the pieces together. So topology is a study of manifolds, and two manifolds are topologically equivalent if they can be smoothly deformed into each other. So on the left-hand side, I'm showing like a strip of paper, which I've taped the ends together of. And if I take that strip, I can squeeze it together. It doesn't have to be a circle. It can be many different shapes. These would all be topologically the same. Now, on the right is the Mobius strip, made an appearance. And if I take my original strip, cut it, twist it, retape it, I'll get the Mobius strip. The Mobius strip is not topologically equivalent to my original strip because of the cutting and the taping. Those are not smooth deformations. They're very abrupt. I have to kind of rip it apart and re-glue it. So this is an example of two manifolds which are topologically distinct from each other. The classic example that shows up a lot in slides by condensed matter physicists studying topological insulators is the donut coffee cup. You can make, if you think of making this out of clay and you had your coffee cup, you could kind of deform the clay to push the top down and make the handle a little wider, and you could turn it into a donut. And these things are topologically equivalent because they both have what's called a genus. They both have one hole here, and that's what makes them be smoothly deformed. In contrast, if you tried to make a pretzel, you'd have a problem. You'd need to poke some other holes. And so hopefully this gives you some intuition of what topology is about. It's about studying things that can be smoothly deformed into each other. And in some sense, we want to make different equivalence classes of whatever object we're talking about. And this, it could be balls of clay, it could be our paper strips, it could be whatever we want. And we want to put them in equivalence classes. Those that can be smoothly deformed are in one equivalence class. We don't care about the precise details. We only care, for example, about, how many holes does it have. So now, how do we apply this to our band structures? Well, we can make equivalence classes of band structures. So this is kind of a trivial band structure because all the bands are flat. This is what would happen if my atoms were very far apart from each other. If they didn't hybridize at all, then the levels of the crystal would just be my atomic orbital levels. There'd be no bonding and anti-bonding. Once you start bringing them closer, bringing atoms closer together, you start getting this, you start getting a shape, which is kind of that cosine curve that I was showing before. And so we can say that all of these four pictures, these are all band structure schematics that are topologically the same as each other, because I've just taken the bands and just moved them around a little bit. But in all of these pictures, these are all insulators. Say if my filling, I'm kind of assuming the filling is half filled. They're all insulators because I always have this finite energy gap. And so the crucial point here is that I never close that energy gap. That's the cutting and the re-gluing that I'm not going to do. So the smooth deformations are I maintain this gap. I can do whatever I want to the energy bands. I can even make the ones down here cross as long as I never close this gap. In that way, we can identify band structures and we can put them into topological classes. Those that can be smoothly deformed, and then others that can't, but maybe they can be smoothly deformed into each other. Notice we can only do this for insulators. We can't really do it for metals because we don't have this gap to talk about. Right, so this is my point. The metals don't have these two different groups, and our topological equivalence is like we could pull out the strands of pasta in any way, but we just don't allow these things to touch. So now we can get this notion of a topological insulator. So conventionally, kind of in the heuristic that I was trying to sketch, every band in our band structure is associated with an orbital. In our topological insulator, what happens is that that's not true. There's certain insulators which would be 99% s orbital in a band, and then have like 1% p orbital. And the point is that I can never smoothly deform this into this. If I try to do that, then I have to go through a transition where this energy gap closes because the p and the s orbitals need to exchange back. So, I don't know if there's a lot more kind of details to say, but I think this is the best heuristic. The idea is that these things can't be smoothly deformed to these, And you have to take on faith right now that there are examples of this. And naively, people originally thought all insulators had this perspective. They thought every insulator I can think of as filling up energy shells to some level, and then once I'm filled, that's it. And it turns out that there's certain insulators that don't have that property. They're not a filled one type of shell. The orbitals are hybridized in a weird way that mixes the different types of orbitals, and therefore this type of insulator is distinct from this type of insulator. And importantly, if I try to deform them, my energy gap closes. And where an energy gap closes, this thing becomes a metal. So I can't get from one insulating equivalence class to another equivalence class without becoming a metal in between. Okay, good. So that's kind of our definition of topological insulator. And now we want to connect, how did this definition relate to our original definition? So I told you all this stuff about surface states, and it's not clear that this has anything to do with that. And so the way that we get surface states is the following. Suppose that I had a conventional insulator and I put it next to a topological insulator. As I was just showing, the bands, which remember these bands just correspond to hybridized orbitals, you can't smoothly deform them without becoming a metal in between. And now when we put these things next to each other, like as a function of space, the orbitals will try to deform. You have a bunch of orbitals on this side that make this insulating energy bands. You have orbitals on the other side that make these insulating energy bands. But as they get close to each other, what are the orbitals to do? Well, they have to kind of merge in some way, but we know that they can never merge without closing the energy gap. That's what made them in topologically distinct classes. And so that energy gap will kind of close somewhere, and it closes on the boundary. And that means that you have a metal on the boundary. So basically, in this picture, I'm kind of showing something abstract, which is I have two different materials, and if I tried to change parameter space, I couldn't get from here to here without becoming a metal. In this picture, I'm saying, well, why don't I actually do that as a function of real space? I take material A and material B, and I put them next to each other. And far away from the boundary, they should each behave as though they're isolated. But close together, we have to go through that transition. And precisely because they're topologically distinct, and we define topologically distinct to mean that you can't be connected without having a metallic phase transition, that transition is happening at this boundary. So I hope that that gives some intuition of how to connect these pictures. We can think phenomenologically of the topological insulators having surface states, but where those surface states come from is from the band structure. And I guess I should say that air is a conventional insulator. So that's the connection where I think about the surface of my topological insulator. I think of this as just being air, and at the surface of this, for the electron orbitals to kind of smoothly connect to the vacuum around them, they have to make a metallic surface state. Yeah?
So you have to put different atoms into a topological insulator to make it turn into.
Yeah. So basically, actually, the way that this is done is that there's just certain compounds that are topological insulators that, like, you look at their band structure, you could compute it, you see it's an insulator, but if you look at the orbitals that correspond to those insulating bands, you'll see it just is a topological insulator. So we don't make it by putting electrons in a weird way. There's certain crystals that are normal insulators, and there's certain crystals that are topological insulators, and they exist in nature. We can also make kind of weird heterostructures by making new materials that don't naturally exist in nature. But again, that would be classified in one or the other. So it's not that we're doing something weird to the electrons. It's just that how the orbitals hybridize in that crystal is in this way. Yeah.
What happens if we smash give it some momentum at one point?
Yeah. So basically the electrons on the surface, if you give them momentum, they'll have the kind of weird properties that we talked about. You know, I sketched them for you. I didn't justify them, but the weird properties that we have before. If you looked at the quantum Hall edge and you give an electron momentum in a certain direction, it will flow. If you try to give it momentum in the opposite direction, it won't flow. So it has those properties. Yeah, is there a question in the back? Yeah.
So in the earliest, like in one of your early
Yes.
slides, you showed an example of a topological insulator, and I couldn't see from back
Yeah.
here, but I was looking to see what compound it was.
Oh, yeah. Mhm.
At B and then something.
Bismuth selenide. Yeah.
And so that's a natural one, like a
Yes,
naturally
exactly.
occurring.
Yeah.
And it's bismuth and.
Yeah. Bi2Se3. Bismuth selenide.
Okay.
Yeah. That's just one example, but yeah.
Okay. That's when you said that, I'm like, well, I think she had one up
Yeah.
there. Yeah. And so that's naturally occurring.
Yes.
Okay. Cool. Thank you.
Yeah. Question in the front? Yeah.
I'm not sure if my question even makes sense, but can you make devices using this phenomenon?
Yeah. That would exactly be the idea. So basically, I mean, first off, every crystal that you make always has an edge. So you'll naturally have these edge states flowing, but maybe you want to control them in a certain way. And so you might make boundaries between certain types of crystals. You might, you could also make, like an array of dots where you'd have kind of edge states which are moving around. So you can play around with, making, like heterostructures, which is to say you combine different types of crystals and put them next to each other. And if you can do that in a controlled way, you can control roughly where the edge states will flow.
And they would be different from a conventional semiconductor.
Yeah, well, they're basically a different type of semiconductor device. Yeah, and yeah.
Are there any relationships to superconducting with this?
There are some, yeah, actually there are, because we can also identify topological superconductors, which will also have edge states. So this paradigm extends to superconductors also. Yeah. Yes?
Could you tell us the name of the software that you said that people will play with? Is that free or?
Yeah. There's a few different yes, so a couple things to say. I think it would be difficult to it's not the sort of software that you can just like pick up and use immediately, but there are some free versions. I think one of them is called Quantum Espresso. And I think that's one of the free versions. So yeah, I'll leave it at that. But let me go on actually, because I'm gonna also show you something related to that question. So I think I'm over time. Let me just show one more thing, which is I wanted to give a little flavor of some recent research topics that other people have been working on. One of these questions was, how does crystal symmetry impact topological phases? So crystals, we've been drawing this kind of cubic crystal. I haven't said much about crystal structure. Crystals exist in many different forms, and you can keep combining different types of atoms. There's infinitely many possibilities, and they have different types of symmetry. So we were wondering, how does the crystal symmetry impact the possible topological phases that you can get? And one of the outcomes of this is we made, me and my collaborators, we made this website. So this is actually a database. And what this website does, this is a screenshot from this website. So you can click on this website, it will show you different atoms. So you could click on different names of different atoms, and it will give you a list, which is coming in this video, of all the different known compounds that have this combination of atoms. So in this example they picked, there was only one, but it'll give you a list. And then it will show you, here's the crystal structure. It shows you something called the Bruin zone, which we haven't talked about. But then as this video keeps going on, it also shows you the electron band structure. So for any known material, you don't need to calculate it yourself. It's been calculated. So yeah, so then it comes down to this. And actually for our purposes, we are trying to find these different topological phases, but this concept of having a database with all these band structures, that's been around for a while. And there's a really nice website called Materials Project, where if you go to Materials Project, you need to log in with an email account or make an account there. But if you go to Materials Project, it does something like this, way before we did it, because they weren't looking at topological properties. You can just pick different elements, you pick your compound, it shows you here's the band structure of this compound. So you should be able to put in like those plots of gold and diamond I got from this website, but you could also get them on Materials Project. And you can kind of check your intuition about which materials are metals and insulators. Yeah, so I think that's a really neat and free resource. Okay, and then I should just stop. So these are kind of some directions, and if there's something that caught your eye, then you can ask me a question at lunch. I'll be here all day, and this is a summary of what we talked about. Yeah, I can take a question.
Is there anything that has to do with Bose-Einstein condensate that you were talking
Yeah, so not really, but Bose-Einstein condensates are, that's an example of a superfluids. Yeah, so basically, I've been talking, at least implicitly, about solids, which are made of atoms. Bose-Einstein condensates are made of atoms which will behave as bosons, and bosons can condense. And so it kind of leads to a different type of phenomenology than I've described here. Yeah.
Maybe I can add a remark.
Yeah.
We were instructed that we will ask you to ask questions through microphone so that it will be recorded. Yeah.
Yeah, sorry.
There, please. I'll get you.
Surface states have been known for a long time, and one of the critical aspects of the difference in the surface band structure compared to the bulk is the rearrangement at the surface.
Yes.
So how much does that play in these single compound materials like the bismuth, telluride, or selenide?
Yeah.
Is there a strong rearrangement of the surface that gives rise to these topological?
So let me say two things. So of course, you're 100% correct. Surface states have been studied for a really long time, and what distinguishes a topological surface state will be distinct from say a surface state on an insulator that comes from atoms or electrons rearranging. And it will be distinct precisely because the current will flow in these kind of, weird ways depending on what dimension that you're in. Now, the second part of the question is, well, does this surface reconstruction happen on, say, bismuth selenide or bismuth telluride, which is another topological insulator? The point here is that no matter how the surface reconstructs, you still need to have this surface state. So the surface band structure will change, but you won't be able to get rid of the surface state. And that's kind of the special robustness of it. If I had a normal insulator and I had metallic surface states, there would exist some surface termination that would be insulating. But here you have the surface state and you can't get rid of it, and it has different properties. So that's how you make the distinction between them. Yeah.
Please.
If we have students that are interested in topology, how would you describe or recommend mathematical courses for them to take?
That's a good question. I didn't really learn about topology until I was in college. So what is a good resource for younger people?
Is there any specialized courses or background that would help them out?
I guess what I would say is if you want to learn about topology, then you should take, you should major or minor in math and take all those pre-courses. Okay. One thing I could have put in a plug for is there is at least some online course on topological insulators. It has videos, but it also has, it has a website with a video. So you can read or you can watch or you can do a combo, and they have a couple questions. And it's really like 1 page per topic. So it's, it's not a textbook. It's really kind of meant for, I wouldn't say it's meant for high school students. I would say it's meant for advanced undergrad students. But of course, there's some, some high school students that will benefit from seeing that, even if they aren't really prepared to digest all of it. So maybe I can look up that website and try to find it for you afterwards. That would be an interesting introduction to topological insulators, not the mathematical field of topology, but it gives some insight into that.
Okay, I think there was another question.
Just as an aside, my younger brother took a class in differential topology at Cal. Okay, so I know it's offered. Yeah. But all he said was hellaciously difficult. Yeah. That was his term for it. So they do offer it. Yeah. Maybe not now, but. Yeah.
Could you just speak a little bit about the implications for quantum computing from this? You said a little bit before, but if you just want to go off and tell us what could be done.
Yeah, so like I said, there is this kind of proposed platform for a topological quantum computer, and it's definitely in its infancy compared to other platforms for quantum computers. So this is, I think, more of a a long shot idea, which is which is being investigated by Microsoft, and they now move their research institute to Goleta, which is, you know, the town that the hotel is in, right down the street from UCSB. So so that's a kind of active platform that's being studied, and I didn't really explain how this relates to what I've said here, but the basic idea is that just like I was talking about edge states being robust to disorder, if you have a topological insulator and you look at excitation, so what that means is you have a ground state, but you have some excited states that maybe you can excite locally, they will also have a kind of robustness. And so the point would be that you could make a qubit which would be robust to disorder. And what disorder also means is like local temperature fluctuation. So the problem always in a quantum computer is, and you have the same problems in classical computers, but if you store data, you want it to be stored and stay in the way that you want it to store it. And so if there's kind of different types of disorder, and however you've stored your data, you can kind of flip from, say, 0 to 1, or spin up to spin down, depending on whether you're talking about a classical or quantum computer, then that's going to be a problem. And so the idea was that these topological excitations are more robust, and so they could be a more robust platform for a quantum computer. But of course, the challenge is always connecting the theory to the materials devices. So in principle, you're more robust, but in practice, maybe you have too much disorder that you can't overcome it. Maybe you haven't found the right material that's realizing the phase that you want. So there's kind of, because I should say that there's a whole zoo of different types of topological phases, and the ones that they want for the quantum computer are very particular type. And so they're trying to engineer different platforms to realize that. And I think it's challenging, but exciting.
Great.
The idea of graphene being a big thing and doing a lot of work with this.
Yeah.
Is there a connection or ties in between the two?
Great. You really gave me a great question here. I'll try to answer it. So it's really interesting. So graphene by itself is a semi-metal. It's kind of halfway in between an insulator and a metal in a different way than this. It's not about the edge states, but its band structure crosses, so it has very few electrons kind of at the Fermi level. So one of the first proposals to realize a 2D topological insulator was actually in graphene. So graphene has almost zero spin-orbit coupling. But if you pretended that graphene had more spin-orbit coupling, then it would change the band structure of graphene. I really want to draw something, but the graphene band, there's a little bit of board. I don't think people can see it, but I'll just say the graphene band structure, look, we call it a Dirac cone. It crosses like this. If you introduce artificial spin-orbit coupling, it opens up a gap and makes it into a small insulator. That insulator would actually be a topological insulator. So the very first paper called Topological Insulator was about hypothetical graphene with spin-orbit coupling. And this comes back to the interplay between theory and experiment. The theorists can make hypothetical graphene, but the experimentalists have real graphene. And so then there was some ideas of, well, can I take other materials with large spin-orbit coupling and put them on top of graphene? So graphene would kind of inherit some of that, because when you put two materials next to each other, they kind of combine their properties in some way. So there is some work in trying to make topological insulators out of graphene, and I don't think that that's really panned out in a really effective way. Instead, it turned out that there's some other platforms that turned out to be better at realizing topological insulator.
Right. I think we do have some participation online, and I want to make sure that if there's any question, that's not ignored. There was one in the middle of Jen's talk. Craig, I guess we don't have any, right? Okay, good. Any further questions or comments? If not, I think we're a few minutes early, but we'll stick to the schedule. We'll come back at 10:55. All right? Thank you, Jen.